So in this video, we're going to talk about Hamiltonian path in Hamiltonian circuits. So far in the last 3 lectures, we look at different ways that you can move around places and objects depending on what you need to do. In the first lecture, we learned how to read the graphs that you probably find in puzzles. So this graph, as you can see, don't have the x value or the y value or the x-axis or the y-axis as you see in calculus courses. The graphs are made of vertices and edges, and the vertices represent places you want to visit, and edges represent different ways that you can get to the vertices. You can think of this as houses and streets that connecting them. And so far, we try to look for different ways to move around this type of graphs that can help us solve problems. In the last video, we looked at Euler path and Euler circuits. The idea of Euler path and Euler circuit is that you try to visit each edge exactly once and only once. Now in this video, we're going to talk about Hamiltonian path and Hamiltonian circuit. For Hamiltonian path, you visit every vertex exactly once and finish anywhere. And for Hamiltonian circuit, you visit every vertex exactly once and you finish back where you started. So I would like to make a table to compare the type of algorithms that we know. So in the last video, we have Euler path and Euler circuit. For Euler path, you visit every edge exactly once, and you can finish anywhere. For Euler circuit, you also visit every edge exactly once, but you finish back where you start. In this video, we're going to look at example related to Hamiltonian path in Hamiltonian circuit. This is Hamiltonian circuit. So for Hamiltonian path, you visit every vertex once and finish anywhere. And for Hamiltonian circuit, you visit every vertex once and finish back where you start. Not every graph has an Hamiltonian or Eulerian property. It's just that when you see a graph, there's potentially 4 different algorithms that you can identify. So that's the remark that I want to give you. That is, for each undirected graph, there are 4 potential outcomes. To determine. Now another remark that I want to give you is that if a graph has a Hamiltonian circuit, then it has a Hamiltonian path, very similar to the case of Eulerian path and Eulerian circuits. That is, if a graph has an Eulerian circuit, it has an Eulerian path. However, the reverse direction is not always true. So if a graph has a Hamiltonian circuit, then it has a Hamiltonian path. So the reverse direction is not always true. So I'm going to give you some example where we're going to look at the graph and identify if we have Hamiltonian path, Hamiltonian circuits, and possibly Eulerian path and Eulerian circuits. So consider the following graph. I'm going to write down the solutions for Hamiltonian path and Hamiltonian circuits. As before, there should be multiple solutions to this one problem. And similar to that, for the case of Eulerian circuits, there should be multiple solutions to that. You just need to give one solution out of the many. For Hamiltonian path, you can start from E, then go to D, then go to C, then go to A, and then finally go to B. So as you can see, for Hamiltonian path, you visit every vertex once, and you can finish anywhere. So I start at E and I stop at B. So here you visit every vertex once, and you finish anywhere. And this is how you travel. You start at E, you go to D, D you go to C, C you go to A, and A you go to B. And as you can see, we didn't use this edge, and this edge. Right? We didn't care about how many edges that you visit. We just care about visit every vertex once. Now for the case of Hamiltonian circuit, so the algorithms say that you can visit every vertex once and finish back where you started. I'm going to start with the vertex E again. So E, we go to D, we go to C, we go to A, we go to B, and we get back at E to complete the circuit. So this is how I travel. That is E go to D, D go to C, C go to A go to B, and B go back to E. For this exact graph, you can also be able to identify the Eulerian path in Eulerian circuits if you want to, and you can calculate the degree of each vertex in order to identify if there exists an Eulerian path or an Eulerian circuits or not. So in this case, let's quickly do the calculations. For the vertex A, the degree of the vertex is 2. For B, the degree of the vertex is 3. For E, the degree of the vertex is 3. For D is 2. For C is 4. Since we have exactly 2 vertices of odd degree, this graph represents an Eulerian path, but not an Eulerian circuit. And for Eulerian path, or Euler path for that matter, here's one of the solutions. You can start with E, then go to D, then go to C, then go to A, then go to B, then you go back to C, then go to E, then from E you go back to B to visit all the edges, exactly 1. So you can write down the edges here. So from, let's say this is E1, this is E2, this is E3, this is E4, this is E5, E6, and E7. So here E1, E2, E3, E4, E5, E6, and E7. So again, the idea of the Euler path is that you want to visit every edges only once and finish anywhere. For Eulerian path in Eulerian circuits, we don't care about how many times we visit a vertex. For this example, we visit E twice, we visit C twice, and we visit B twice. Well, we don't care about that as long as we cover every edge only once. So I mentioned earlier that not all graphs have an Hamiltonian circuit or path. So the difference between Hamiltonian path and circuits compared to Eulerian path and circuit is that there is really no way to tell just by looking at the graph. You cannot calculate the degree of the vertex to identify if there is Hamiltonian path or Hamiltonian circuits. What you need to do is that you must have to do the trial and error to determine if there exists a Hamiltonian circuit or Hamiltonian path. And this makes it more difficult to deal with Hamiltonian path and circuits scenarios. So here's another remark that I would like to give. One remark is that not all graphs have Hamiltonian circuit or path. The second remark is that you must do trial and error to determine if there exists a Hamiltonian circuit or path. So you must do trial and error to determine if there exists a Hamiltonian path or circuit. Now I'm going to give you a couple more examples. Again, the idea is that you have to do trial and error, and when you do actually do the problem, you have to start at one vertex and then go through with the algorithm of Hamiltonian path and Hamiltonian circuits to see if they're really in Hamiltonian path in Hamiltonian circuit or not. So in this example, you have a Hamiltonian circuit. By the remark that you see earlier, when a graph has a Hamiltonian circuit, it also have a Hamiltonian path. Again, the reverse direction is not always true. So from here, you can write down a Hamiltonian path. Again, you can start anywhere you like for a Hamiltonian path, as long as you visit every vertex once and finish anywhere. So I'm going to start at A, I'm going to go through B, I'm going to go to C, I'm going to go to D, and then from D I go to B, and from B I go to E, and I stop there. Right. Now for Hamiltonian circuit, you can start anywhere again, as long as you visit every vertex once and finish back where you start. So I'm going to start with B and see where we go with it. So B, you go to D, then go to C. From C, I go to A. From A, I go to E. And from E, I go to B to complete the circuit. So that, again, one of the solutions for Hamiltonian path and Hamiltonian circuits. Now I'm going to give you another example. In this example, you don't have a Hamiltonian circuit, you only have a Hamiltonian path. And again, this has done through the trial and error in order to determine, again, if there is a Hamiltonian path or Hamiltonian circuit. So for this problem, I only have Hamiltonian path. So I'm going to start with A. I'm going to go to B. From B, I'm going to go to C, then go to D, then go to E, then go to J. From J, I'm going to go to G. From G, I'm going to go to I. From I, I'm going to go to F. From F, I'm going to go to H. And I had just completed the Hamiltonian path. So this is how you go. You're going to start at A, you go to B. From B, you go to C. From C, you go to D. From D, you go to E. From E, you go to J. From J, you go to G. From G, you go to I. From I, you go to F. And from F, you go to H. Right. And that's what you got for the Hamiltonian path. There's no Hamiltonian circuit, as you can see. If we continue with H and you go back to J, you violate the Hamiltonian circuit requirement. And that's it for Hamiltonian path and Hamiltonian circuit. Please let me know if you have any questions. Thank you.